Welcome to the GeoMethod channel. Today we are solving another interesting geometry problem. Here is today's challenge. Can you find area of the green shaded triangle? Take a moment to study the figure. Then let us uncover the key geometric ideas that make the solution click. The outer figure is the square ABCD with area 100, and its diagonal AC is already drawn. Our target is the area of the green triangle AEF, tucked against the top side. Let us pin down every length before we compute. A square's area is its side length squared, so the side is the square root of 100, which is 10. Every edge of square ABCD measures 10 units, and that 10 will drive all of the arithmetic to come. Point E rides on the diagonal AC, the line running from the top right corner A down to the bottom left corner C. Because E is locked onto that diagonal, its height will be tied to its horizontal position, which we will use in a moment. Point F lies on side BC, and segment EF is perpendicular to segment BC. The drawing makes segment EF the horizontal leg of a 45 right triangle. The diagonal AC starts at height 10 at the top corner A and falls to height 0 at the far corner C over a run of 10. So it drops exactly 1 unit of height for every 1 unit of horizontal distance. That constant slope is the key relationship. Let the distance from corner B to F along the left side be x. This single unknown will fix the position of F, and with it, the position of E and the whole configuration. Triangle EFC is a 45, 45, 90 triangle, so its two legs are equal. Both segment FC and segment FE equal 10 minus x. Our first insight is this. Both triangles share the same base segment, EF. The apex of the green triangle is corner A, sitting on the top edge at horizontal position 0. The horizontal base segment, EF, stands at horizontal position x, so the perpendicular distance from A across to that base is exactly x. Area is 1/2 base times height, with base segment EF equal to 10 minus x and the width from A equal to x. The green triangle AEF has area 1/2 times x times 10 minus x. Call this our first expression. Now the other triangle. Its apex is the far corner C at horizontal position 10, while the base segment EF still stands at position x. So the perpendicular distance from C across to segment EF is 10 minus x. Same base 10 minus x, but now the width is also 10 minus x, so triangle ECF has area 1/2 times 10 minus x squared. Call this our second expression. Notice both areas carry the factor 10 minus x. The problem tells us triangle ECF is twice the green triangle AEF. This single fact is exactly what we need to lock down x. Let us feed our two expressions into it. Substitute 1/2 10 minus x squared on the left and 2 times 1/2 x times 10 minus x on the right. The geometry has now become a single equation in the one unknown x. On the right, 2 times 1/2 is just 1, so the right side collapses to x times 10 minus x. The equation is now 1/2 10 minus x squared equals x times 10 minus x, cleaner and ready to cut down. A second insight now finishes the structure. The common factor cancels before solving x. Multiply both sides by 2 to clear the fraction. The left becomes 10 minus x and the right becomes 2x. We are one short step from x. Add x to both sides to gather the unknowns together. 10 equals 2x plus x, which is 3x. The equation is now trivial to finish. Divide both sides by 3, and x is 10/3, about 3.33. That fixes f exactly 1/3 of the way along the left side from b, which matches the picture. Feed x back into the base. Segment EF is 10 minus 10/3, which is 20/3. Now every length in the green triangle is pinned down, and we can measure its area. Put the numbers into our first expression. 1/2 times 10/3 times 20/3. That is 100/9. The green triangle AEF has area 100/9. Let us check. Triangle ECF is 1/2 of 20/3 squared, which is 200/9, exactly twice 100/9. The 2-to-1 condition holds, so our solution is consistent. Thus, area IEEF is A and area EECF is 2A, exactly matching the given ratio. The green area is 100/9. That completes the solution. A good geometry problem often has more than one beautiful solution. If you see a genuinely different construction, a high-level idea that leads to another solution, or a thoughtful adaptation of an existing method, share it in the comments. Even a rough idea is welcome. A sketch of the key move is enough. We greatly appreciate these contributions. With your permission, we may feature the approach in a future Viewer Solutions episode and acknowledge you by name or channel handle. Thanks for exploring geometry with GeoMethod.